So to close out tonight's program, I want to tell you a little bit about galaxies and what they are. We often talk about galaxies, and we don't give you much background information. We speak about them like you all know what a galaxy is. Of course, this is a famous Hubble Deep Field image, and you see mostly galaxies in this image. There's spiral ones, there's elliptical ones, there's odd-shaped ones. They come in all different, shapes and sizes. But what are they really? Well, let's take up some close-up images. Here's a beautiful spiral. You can see the spiral pattern's pretty tightly wound. You can see the bright, hot, young blue stars that are in there. The dust that's in the foreground blocking out the light from the background, and sort of that orange-colored light coming from the bulge in the central regions of that galaxy. Here's another one. This looks a little different, although this is probably a very similar galaxy to the last one, but just viewed edge on. So, but anyway, I'm still talking about these things like you know what they are. What are these things? Well, they're collections of stars out in space. Stars, gas, dust. The gas gets fused together to form new stars. If you have a dense enough pocket, you can make new stars. Blue stars don't live very long, and that's why I call them young. So those blue spots you're seeing in this image tend to be very, very young stars that have just formed. And the dust is blocking out that light. So we can see that it's all kind of down there in a disk. Now, there are probably hundreds of billions of stars like the sun in this galaxy. And I mean, some of them are larger, some are 50, 60 times more massive, some are 10 times less massive than our sun, but they're all kind of similar. They're just big, glowing, plasma balls that are fusing elements into heavier elements that makes them hot and glow. So how did they get that way? Here's the edge-on view of a spiral. You can see that dust blocking out the starlight again, and it probably has a spiral pattern if you could view it from up above. Kind of like this, maybe. This one has a beautiful spiral pattern as well. That dust blocking out the lights, the bright blue stars, kind of the orangey light in the middle. You're kind of seeing a pattern here. Are all galaxies like this? Well, not really. Here's two that are kind of close together. In fact, the one in the upper right probably, we think, flew past the one on the left, and it triggered sort of an interaction between these two. These galaxies are close enough together they're interacting. This is the famous Whirlpool Galaxy, or M51, by the way. So, again, very, very large objects. But they're not all spirals. There's a spiral in the upper left or upper right there in the corner. So again, hundreds of billions of stars like the sun, and gas and dust making new stars. But then you have this thing in the lower left. It looks very smooth. It looks kind of just a whitish, a yellowish white color. Well, that's an elliptical galaxy. You can see it's kind of elliptical in shape. It doesn't have a lot of dust, doesn't have a lot of gas. It's not forming any new stars right now. And it just gets brighter and brighter and brighter towards the center. Here's another elliptical galaxy. In fact, this one has a black hole in the center and a jet. This is M87 from the famous Virgo cluster from our very own big picture in the Gunther depths of space at Griffith Observatory. So another giant elliptical galaxy. And this one contains even more stars than our own Milky Way. Ellipticals can be immense. They can be many times larger. But not all galaxies are organized either. Some are just kind of messy. This one's making some new stars, but it's not very well organized. In fact, it's kind of classified as an irregular. We would call this irregular. And some irregular galaxies are very small. They can be 10 times, 20 times, 100 times smaller than our own Milky Way. So they will still contain millions to billions of stars, but not hundreds of billions or trillions. So these collections of stars out in space, not huge distances in between them. Galaxies can, maybe be 5, 6 galaxy sizes in distance apart from one another. But what is going on? Why do they end up this way? What determines a galaxy's shape? On the left, we got an elliptical. On the right, we got a spiral. Why did they end up that way? Do we have any clue? The answer is, well, maybe we do. But first of all, what are some of the properties? Spiral galaxies, they tend to be, well, they can be very, very young, to 9-ish billion years old. We've seen some that are older, very far away in the early universe. We've seen some that appear to be spiral shaped. Their sizes go from, well, 5 to 100,000 parsecs. That's a kiloparsec. Now, what the heck is a parsec? Well, a parsec is 3.26 light years. A light year is not a measurement of time. It's a measurement of distance. It's how far light can go in a year. So you're talking about something that is, 300,000 light years across or more. So they can be pretty big. But now let's go over to the ellipticals on the right-hand side. The age range 7 to 10, so maybe they're not quite as old as the spirals, strangely enough. Some of the spirals can be older. Their sizes get from much, much smaller than a spiral galaxy to much bigger, 2, 3, 4, 5 times bigger. In fact, I wrote 200 there, but they can be even huge when you find these giant ellipticals. Now notice, spirals are kind of in the middle of the range of the mass, from about 1 billion solar masses to what is that, 10 to the 12 is trillion, I guess, solar masses to, well, 10 to the 7 to 10 to the 13. So ellipticals can get even larger than those spiral galaxies, but also can be much, much smaller. So ellipticals are weird. They're the smallest, but they're the biggest. They're the least massive, but they're the most massive. So what's going on here? Can we figure it out? Lots of gas and dust in the spiral galaxies, not much at all in the ellipticals. And the spiral galaxies are forming stars right now, and you don't see much at all in the ellipticals. So what does that tell us all? Can we figure out why that would be the case? Well, first of all, just you can classify the galaxies, like I said before, elliptical, spiral, and irregular. Irregular ones are almost like spirals that don't have any structure to them. They're doing a lot of the same stuff. So we're going to kind of set those aside for the moment as we move forward to think about this a little bit. Can we organize them into some sort of pattern? Well, originally, Edwin Hubble thought, well, let's put a classification like this. It was called Hubble's tuning fork diagram. You can see why there. It looks like a tuning fork. And the thought was, well, maybe, just maybe, these ellipticals have, they were in the process of turning into spirals. And now they had to split the spirals in half because some of them have that kind of bar-like structure going across the center. We didn't really understand why that was the case. This ends up being completely wrong. Ellipticals are not turning into spirals. In fact, it might be the other way around, actually, in reality. A more current tuning fork diagram is a little bit like this these days, which is a complete mess. You've got strong bulge, that's that central region. You've got weak ones, you've got irregulars. This is from the Spitzer Infrared Nearby Galaxies Survey. They went in and found all sorts of different galaxies, all sorts of different shapes, all sorts of different morphologies, which is kind of the different structures within the galaxy. It isn't helping me at all trying to figure out how this happened, however. So it doesn't seem to be an easy story of one galaxy type just turns into another one. I think we need to look at environment. We need to look and see where these galaxies hang out. Well, they do hang out next to each other. They are found in clusters. Galaxies are in clusters. And just like stars in a cluster, they are orbiting each other. These galaxies orbit one another and they interact with one another. And in fact, as you're traveling through a cluster, you can have your material pulled out. You can have your gas stripped out and be left with just stars behind. So the living in a thick, rich environment like this with lots of other galaxies can affect what you end up like. You might also collide with another galaxy, and we'll talk about that in just a couple of minutes. So environment can have a lot to do with it. But first of all, just spiral structure. Spiral structure for a long time was thought it occurred because it was winding up. If you just have the stars in the middle rotating faster than the ones on the outside, or revolving faster, not rotating, but revolving around the center faster, the galaxy will tend to twist up this way. It'll kind of, just like twirling some yarn, it'll get tighter and tighter into that spiral. Well, we don't see that. Galaxies near us are not more tightly wound up than the ones far away. And in fact, this should happen so quickly that it would rapidly wipe out any spiral structure. So that is not how spiral structure is found. We think spiral structure comes from a density wave. It's a little bit like getting stuck in traffic. These stars are moving through this disk in this galaxy. They come upon a little bit of a denser area. And as you can see here, they get pulled into it quickly and they hit that denser area and they slow down. It's like getting stuck in the traffic jam. You work your way through the traffic jam and then you're on your way again. So these are sort of self-reinforcing traffic jams. Let me rerun that because it is just kind of a fun simulation here. So you can see down in the center, the stars are moving the fastest. They go in and out of these dense regions, but the dense regions are self-propagating. And indeed, the spiral does slowly move forward in the same sense that it's wound. So the pattern moves, but the stars are moving faster than the pattern speed. We've modeled this, we've done simulations, and indeed we think that's how that happens. Now, we have modeled the formation of a galaxy. You can see here, this is gas flowing down into the center of a galaxy, moving in very, very fast. And let's see if we can end up with something that looks a lot like a spiral galaxy. They've taken the physics of gravity. They've put it in the dark matter, the extra stuff that is needed to hold everything together, and then they run the simulation. And this is just physics. Physics and what we think we understand about the universe, they turn it on. So let's see if we end up with anything that looks like a galaxy. So far, we've got about 4 million suns is all, 5 million suns and stars. There's a lot of gas. We're only about 4 billion years after the Big Bang. So we've got a little while to go here. We're still pretty early in the universe. Lots of gas is flowing in. You can see some dense pockets heading in there. Now we're going to get a different angle here. Now, what is that? That looks like a spiral structure down in there. The physics naturally formed a spiral structure down in the center down in there. They didn't tell it to do that. They didn't paint the spiral on. It formed naturally through the physics that was just embedded in there. So now more gas is flowing in, more star formations being triggered. And you can even see some dense pockets of gas floating around. Those are probably dwarf galaxies that have formed around the outsides of this bigger galaxy, globular clusters. So we're about 7 billion years after the Big Bang at this point. The Earth has not quite yet formed, by the way. The sun and the Earth, we're getting there soon, any moment now. Okay, somewhere in here. But this is really starting to look like a modern spiral galaxy down in the center there. You have a disk of material. Uh-oh, here comes a neighboring galaxy to mess everything up. Okay, okay, they stopped it just in time for us. All right, before it came in and smashed into it. So that was the Illustrious team again. That simulation we showed at the start tonight was done by the same Illustrious team. They are able to form individual galaxies from their simulations of the universe. Now, you can see here the galaxy on the lower left, redder, probably not making a lot of new stars. The one in the upper right is making a lot of stars, but galaxies do interact with one another. In fact, this pair of galaxies, real image, keep in mind this is real, they're interacting so much you can see tidal features. The tides are when you yank on one side of the galaxy, stronger on one side than on the other, tends to stretch it apart. You also trigger these spiral structures even more strongly when you have an interaction like this. So real image. Now, a whole bunch of other real interacting galaxies. Now, these are not the same galaxies interacting. We can't wait around billions of years to watch this happen. So we're seeing individual pairs in perhaps different phases of their merging. We're not really sure, but they sure look like several galaxies close by interacting. Well, they did some simulations. They went and said, well, let's just turn on a galaxy collision and see if we can make anything like these. So put together some dust, put together some gas, put together some dark matter, some stars, send them revolving, rotate the galaxies. Stars are revolving around the core. Well, there is the real one. There's the simulation. Okay, I could kind of believe that. And this is not new. A lot of you have seen this. This isn't a new simulation at all, but I do love it.
Oh.
Yeah, they're really ripping each other apart.
Right.
The gravitational fields are affecting each other, and maybe it looks a little like this one. Not a terrible match. So we think we're starting to understand why these galaxies have these shapes, why they look weird like this. It's because they're interfering with one another. The physics make them a spiral, but you get these really weird shapes because you're having galaxies colliding. And that was a close match, but not perfect. These big tidal tails, however, we see in the Antennae galaxy.
Yeah.
And they're probably going to show it to us coming up here, I'm guessing. There's a pretty good one, nice match. So it is pretty stunning how closely we are able to do these with just some simple simulations of colliding spirals. Now, it turns out if you take enough spirals, collide them together, and advance this another, several billion years, go forward in the simulation, you can eventually end up something that looks a lot like an elliptical galaxy. It turns out if you collide galaxies together, the gas can shock against itself. It can cause bursts of star formation. It can drive the gas down into the center, and you can end up with an elliptical galaxy. So we think, unlike at the beginning where ellipticals turned into spirals, in reality, it's more likely that some ellipticals we see, maybe not all of them, but some of them were once in a dense region, lots of spirals, and they came and merged together and formed an elliptical galaxy out of that spiral. Now, what you're seeing here is not a galaxy. This is not a distribution of galaxies. This is the afterglow of the Big Bang. Because we wanted to know how galaxies got the way they are. How did they get to this shape? Well, the answer is embedded in this pattern in the Big Bang, believe it or not. What you're seeing is differences in temperature, hot areas and cold areas. Well, some areas are a little more dense. Some areas have a little less material. Where it's denser, that material is going to pull together, and you're going to get more structure. Turns out that that structure grows with the square of the amount of density that's there. We learned that from some guests we had. So you should expect at very, very old times, so that's Z of high numbers, by the way, is a long time ago, and as it gets smaller and smaller, it's modern days, and these are several different simulations. So this is structure you're seeing. Now, this isn't individual galaxies. These are probably chains of galaxies. This is dark matter filaments you're seeing. And you can simulate that. You can have dark matter, turn it on, and that dark matter sucks itself together, forms into these filaments, and the galaxies get embedded along these filaments inside that dark matter. So the dark matter and baryonic matter that forms the stars kind of travel together in these simulations. Now I'm going to move forward in here in the interest of time. We've seen cold disks of gas in the very early universe, believe it or not. So we've seen sort of the makings of a baby galaxy. So these little baby galaxies are out there. The dark matter carries along the gas, brings it together, gets it dense enough, kicks off the star formation, and you can make a galaxy. And the shape of that galaxy is driven by how that gas falls in, how the stars fall in. Now, there used to be a question, was it a big cloud of gas that collapsed in and made a single galaxy, or was it little clouds of gas that all collapsed down and then made the galaxy? Turns out it's a mixture of both, that you probably have a moderate sized thing that does go in and forms the central black hole of the main galaxy, and then you have more little bits that come in. You have mergers, so mergers are very important. So you do get those sorts of things out there. Now, some of the first structures out there, how do they get formed? The bulge of our galaxy that I was saying, that inner part, the disk of the galaxy, are they formed early on? Do they form later? When does that happen? Well, there was a story in the Goods survey, this is the new stuff that I'm talking about here, went in and looked at galaxies and wanted to find out that bulge, the orange glow from the center versus the disky stuff, which is purple in this image. Which formed first? Did you make the disk of the galaxy first and then you made the bulge? Or did you make the bulge and then you made the disk? Well, they went and looked at galaxies a very, very long ways away. And it turned out about a third of the bulges formed early on, and about 2/3 formed later on. So that's a little bit of a mystery. We don't understand why that's the case. This was actually a survey done, Caltech, NASA, Harvard, Smithsonian. And here's some actual images of galaxies. On the left, a natural looking kind of disk galaxy. It's not high resolution, it's far away. Another one in the middle has a well-formed bulge, and on the right-hand side, just kind of a bulge. But why these happened that way, we have no clue. We thought maybe all of them would form early, all would form later, but no, a third and 2/3, that's a little strange. So interesting study by Luca Constantine and others. I'm looking forward to hear more what they have to say about this. And as they dig into it, is there a reason why those third formed earlier? Maybe they're in a denser environment. Maybe they're in a cluster. I'm not sure. So there's more work to be done on that. In addition, we have, of course, the beautiful Alma Telescope. It's an array of radio dishes down in Chile, has made some observations of gas in galaxies in the nearby universe. We want to see, what does it look like? What do the star formation regions look like? Do they all kind of look the same? Or what is their morphology, their shapes? And it turns out they come in all different shapes and sizes, kind of like what we'd expect. But that Alma Telescope is really able to look in and pinpoint where these stellar nurseries are. And they were able to go in and say, no, they don't all look alike. They don't all act the same. They're different, and they're as different as neighborhoods within cities. So, some of them are very well organized. Let me get my pointer here again. So nice, beautiful spiral structure here. Almost all the nurseries are in the spiral region. Here, you've got kind of a nice spiral pattern, but there's some splits to the spiral structure. Here, very stretched out and a lot of star formation right in the center. Here, there's almost a ring going on. Okay, is this Superman's galaxy? What's going on? We got a big guess there. Here is Sauron's eye over on the left-hand side, so rings. These are vastly different, but having the power to simply look at the glowing gas where these stars are forming and strip away those stars and strip away the other confusion, it gives you great power. And that's what they were able to do with this. So we're able to look at that structure of these galaxies in detail and track where these stars are being formed and the behaviors of them. So some beautiful up close images where we added in the stellar light along with that star formation regions, and then some of the black and white images and where they went in with the surveys and sampled them. So this is the FANGS HST Galaxies survey. And the basic idea here is if you observe things with Hubble, if you observe them with ground-based telescopes, if you observe them with radio telescopes, with the carbon-oxygen line, the CO line, you can look at the neutral hydrogen line, you can look at the H1 line. You use all these different powers, it tells you different things about the galaxy. Alma is this sub-millimeter one, and it's actually telling us something about the star formation and how it works. The radio waves can track sort of the diffuse gas. It can look at the gas across the whole galaxy. The infrared can pierce through the dust and can see the stellar nurseries down in there and look at the individual stars forming. The ultraviolet with ultraviolet observatories tells us some of the most massive stars and the high energy. And then lastly, H2 regions, stellar ejecta, supernovae. So really to understand how galaxies form, how they evolve, and how they change, we need the power of all these different telescopes. And it's a complicated business to really try and understand how all this works together. But we're starting to get an idea of it. We really are. The pieces are coming together far better than they used to. And we're starting to get a pretty good picture, to the point, like we showed with our opening simulation. Again, this is the Illustrious Survey, which is getting a little bit old, believe it or not. I'm sure there might even be new ones out there I've missed. But you can turn on the physics, and this is a much bigger chunk of space now. This isn't an individual galaxy forming, but rather clusters of galaxies forming. We showed this with the opening of our show tonight. And they choose the amount of dark matter, the amount of dark energy. Usually those are put into the simulation based off of other studies. So the Planck satellite and others tell you what we believe those numbers should be, what they measure them to be. They put in all the physics of the universe. They put in how they want to have that feedback mechanism as the black holes turn on, as it ejects gas out of these galaxies, how that gas shuts down the star formation. They're able to create a universe in the computer that looks a lot like the universe we live in. And this starts to make us have true belief and faith in the physics and in the understanding that we're starting to get the physics right. We're able to make these simulated universes that look a lot like the real thing. And the other reason I wanted to close with this, obviously, other than saying we have a lot more work to do to really understand cosmology and how it goes, but we're starting to feel like we could be on the right path with some of this. The distribution of galaxies is right, the way the gas flows out and things.